Okay. Welcome, everyone. My name is Mingyu Xu, and I'm associate professor in statistics and data science at the University of Central Florida. I'm honored to chair the session. So in this session, we will have 3 talks on various topics on statistical inference. Each session will have about 18 minutes, and we will have the cumulative Q&A at the end of the session. The audience are welcome to discuss with presenters after the talks. Our first speaker, Dr. Li-Kai Chen, is not here yet. So our second speaker, Dr. Meimei Liu, will be giving the talk in the first place. Thanks, Meimei. Dr. Meimei Liu is currently an assistant professor in the Department of Statistics at Virginia Tech. Her research interests include deep learning, Bayesian data analysis, learning theory, big data analysis, and semi-parametric and non-parametric inference. Welcome, Meimei.
Thank you so much, Mui, for the introduction. And I'm going to share my screen, okay? Yeah. So, as I have mentioned, I pre-recorded my talk, and I would like to show you here. Can you hear it, Mengyu, for the invitation and the organization? And I'm so glad to give the talk at the Women in Statistics and Data Science conference. Today, I will going to talk about the scalable statistical inference in non-parametric least squares. And this is a joint work with my collaborators, Zuo Feng from NJIT and Yun Yang from University of Maryland at College Park. Okay, so basically, today's talk, I will be focusing on inference for large-scale or streaming data. For example, data collected in bioinformatics, including millions of proteins, and streaming data where new and dynamic observations are
Meimei, did you stop sharing screen?
We can't hear you. And your
You're
screen went
muted.
away.
Sorry, let me reshare it again. Sorry about that. Inference for large-scale or streaming data. For example, data collected in bioinformatics, including millions of proteins, and streaming data where new and dynamic observations are generated on a continual basis, like personalized recommender systems, advertising, and healthcare study. So in that case, it may not be necessary or feasible to store all historical data, and we aim to figure out scalable inference tools to deal with such kind of data with complex structure and streaming way. Okay. So just consider the regression problem. We aim to minimize the expected squared loss function L. Here, theta is the parameter that we are interested in. Remember the classical estimation procedures normally based on minimizing an empirical version of the loss correspond to the sample average approximation. But directly minimizing the sample averaging with massive data is computationally infeasible in both time and space. And so in literature, there are a lot of advanced methods to reduce the computational complexity. And today we are going to talk about a scalable approximation algorithm called the stochastic gradient descent to minimize the objective function and get the estimation of the parameter theta. So let's quickly review SGD in Euclidean space. Basically, given an initial value of theta, we want to find a path so that in each update, we can have an increment of theta such that our loss function L can be reduced accordingly. And eventually, we can get the loss function minimized. And here is how we figure out the updating rule. by Taylor's expansion, we can approximate the loss function L theta plus any increment by its first-order derivative evaluated at theta. In the steepest descent, it says that if we can choose the increment direction S as proportional to the negative of its gradient for some small amount gamma, then we can have, if you plug the such S in the loss function, we can see that the loss function actually can be reduced. Therefore, we can update theta in this way. So from this direction, so that we can eventually minimize the expected loss function. Okay, now let's get into or consider the non-parametric regression problem. And we suppose the regression function, we suppose yi equal to fxi plus epsilon I, and we suppose the regression function f belongs to reproducing kernel Hilbert space. And here is the expectation. So here is the expected RKHS gradient. So this is the loss function, and the expected gradient can be represented in this way using the reproducing property. And we can see that in reality, we do not know the expectation, but an unbiased estimator of the RKHS gradient can be represented in this way. That means we can evaluate the gradient at the ith observation. When the ith observation xi and yi arrives, we can evaluate the gradient in this way, and this is an unbiased estimator. And so we have the SGD algorithm, which is proposed by Robbins Morrow in 1951. That it means here, at the ith step, we have the new observation xi and yi, so that we can update the estimate of f by adding the gradient evaluated at the current observation with a learning rate gamma to control the step size. So this is the direction, and gamma I means that on this direction, how much or what's the degree that we want to move for along with the direction. Okay, and the learning rate plays an essential role in the smoothness regularization, and I will talk about this later. Okay, finally, we can use the Polyak averaging by average over the entire updating trajectory to further improve the estimation accuracy. This is our final estimator, and we would like to build statistical inference based on this SGD estimation. Okay, so just as I have mentioned, the learning rate sequence gamma n plays an essential role, and we do consider two kinds of setting. The first setting is about the constant setting. That means I just set the step size gamma as a function of the total sample size. This will be useful when we are dealing with large-scale data that we know the sample size in advance. And another setting is about the online setting. That means we just set gamma I for the ith step. The step size at the ith iteration depends on the ith observation. So this is very useful when we are dealing with the streaming data, that the data comes in a streaming way. Okay, and then so actually for the stochastic gradient descent there do have a lot of work currently, like and the majority of like the parametric related inference or the non-parametric related estimation. But for the non-parametric related inference, such as confidence interval, they are still lacking. And our work will be dealing with this direction. Okay. In particular, we are curious about how confident are we in the prediction of an online learning algorithm, and what is the contribution of the newly arrived data points in online learning? Okay, and so let's consider the constant. Let's first consider the constant step size, and in order to address these questions, we would like to build non-asymptotic behavior for the non-parametric SGD estimator and propose a scalable online inference. So basically, you can just think in this way. In the online setting, for the non-parametric function f star, for any non-parametric function f star within the RKHS, our goal is to construct the confidence interval so that the probability that the f star belong to such interval can be guaranteed with a predetermined level. And also the global inference, that means for any x, we would like to build a level beta simultaneous confidence band for this function f star. This is our goal here. Okay, so now in order to achieve this goal, let's look at our first result. We consider the constant step size because it is easier for us to deviate the theoretical guarantee. We first show in this theorem, that the Kolmogorov distance between the sampling distribution of the standard SGD estimator and a standard normal random variable can be bounded. So this is pretty good. It means that we can always use a normal distribution to approximate the behavior of the sampling distribution of SGD estimator so that we can conduct inference. But before we move on further for the inference, I would like to show you something else. We can see that the variance, the asymptotic variance, it has an explicit formulation. And if you look further, you can see that it is determined by the sample size n and the step size gamma and the eigensystem in the non-parametric in the RKHS space. And another information we would like to deliver is that the total variance, within the total variance, we can characterize for each observation its contribution to the total variance. And we find that for the case observation, it looks like here, this contribution. And we can see that the case observation, its contribution to the variance decreases as k increases. That means the first coming observations play a more important role compared with later observations for online learning. Okay, so this is kind of interesting. That means not each observation does not contribute equally for this algorithm. Okay, and similarly, we have the similar result for the non-constant step size. I will just omit this part here. Okay, but can we use this asymptotic behavior to conduct inference? Unfortunately, the answer might be no, because when we are, as you can see, that the eigenvalue and eigenfunctions are involved in the asymptotic variance, but they are unknown in practice. So how can we solve such kind of challenge? The solution is that we would like to introduce a method called the online inference via multiplier bootstrap. So the key idea means that, okay, it leverages on the online bootstrap's resampling procedure, but instead of resampling from the data, we would like to perturb on the gradient to recursively update the SGD estimates. So in specific, let's look here. Remember, this is the original iteration. And now we introduce the Wn here. The Wn is called the bootstrap sub-Gaussian weight with mean and the variance equal to 1. Then at the nth iteration with observation xn and yn, we would like to repeatedly generate the bootstrap multiplier. And then it means that so we can perturb each time when we generate the bootstrap multiplier, we can perturb on the gradient so that we can recursively update the randomly perturbed SGD estimates like here, so that we can have a sequence of surrogate perturbed averaging SGD estimator. So then we can use such kind of sequence estimator to mimic the sampling distribution of the original SGD estimator. So this is our goal. If we would like this one for this part, this is the sampling distribution of original SGD estimator. But just as we said before, in practice, although we derived its formula, in practice it is not feasible to achieve. But instead, if we construct a bootstrap counterpart, and if their distributions are approached with each other, then we have a solution like we can use this distribution to approach this one, and we can use this quantile to approach its quantile to construct the confidence interval and the confidence band. Okay, so here this is the theoretical guarantee called bootstrap consistency. The bootstrap consistency shows that the original, the difference between the difference of the bootstrap distribution of the difference between the bootstrap estimator, this is a bootstrap estimator, and the original estimator can be approximated or can be bounded. And as the sample size n goes to infinity, then this bound goes to 0. So this is so good. Let me show you some impractical based on this bootstrap consistency, how we can construct the confidence interval. So here, define Q hat beta. We can just define Q hat beta as a conditional quantile that derived from its bootstrap, the supernorm of the bootstrapped estimator and the original estimator. And the bootstrap consistency tells us that for any F star within the archetype space, we can build its confidence band based on the quantile of its bootstrap counterpart. Like here, we first establish the quantile from the bootstrap version, and then we can just plug in this quantile to construct the confidence band. And the honest confidence band, we can show that here the honest confidence band means that we can ensure that the confidence level is asymptotically correct, providing a reliable statistical inference. So here, this is how we construct the confidence interval based on these theoretical guarantees. First, we have, just as we mentioned before, based on the perturbation, we can have a sequence of bootstrapped estimator. And then based on the sequence of estimator, we can provide two ways to construct the confidence interval. One way is called the bootstrap normal confidence interval. We approximate with this sequence, we approximate the variance, and then just as the standard statistics, we construct the interval. Or study, we consider different cases and we compare our approaches with some existing methods for the confidence interval and the confidence band. So your science always performs better, and it always achieves the best. First, it achieves the predetermined level, and secondly, the length of the confidence interval. You can see that it works the best for our proposed method. Okay, bootstrap methods or some offline BSM approaches, the computational time will increase. But for the online, for our developed online SGD-based inference procedures, the computational time is the most efficient one, because for each time when we have arrived at the new data, we just update it instead of refit it. Okay, so I think that's all for my talk. Here is some brief summary. So first, we talk about the uncertainty quantification in large-scale streaming data, and we develop a multiplier bootstrap-based inference work. And here is our paper if you want to look at the details of this method. Thank you, and feel free to pose any questions.
Thanks to Mei Mei for sharing the excellent work. Due to the interest of time, we will move all the question and answer session to the end of the session. So our next speaker is Dr. Li Kai Chen. She is currently an assistant professor of mathematics and data science, mathematics and statistics at Washington University in St. Louis. Please join me welcoming Dr. Li Kai Chen.
Hi, everyone. Can you see my screen here?
Yes, we can.
Okay, great. So thank you for the invitation. So today I will talk about adaptive two-way MOSAM testing for multi-scale change points in spatial time series. So this is a joint work with two of my students, Jackie and Hampton, as well as our collaborator, Michelle. So let's start with the multiple change point detection. So this is a simple univariate time series, and here it's very clear there is, well, two abrupt changes. So this is a very simple example where there is assumed to have two breaks. And such kinds of phenomenon well naturally appears in various different fields. And what we are going to do today is try to consider this kind of problem for high-dimensional time series. Well, for multiple change point detection, a very short review about the previous dominating methods. So first is model selection-based methods like BIC-LaSalle-based method. Another important direction is based on testing, including exhaustive search, binary segmentation, as well as MOSAM. So the last one, MOSAM, is the method that we are going to use today. And what is MOSAM? So MOSAM is, here is a picture to illustrate the idea. So suppose here, this is again, a univariate time series, okay, only one dimension. And well, we are interested to test whether there exists certain changes or not, and we are interested in locate those break locations. And the idea of MOSAM moving sum is just to say that we consider a moving window. So here, look at the U1 here. So this is a time point, and here the Bn here is the window size. So we just consider a window with window size Bn, and we move the window from the start to the end. And we look at the left average versus the right average. So if there is a mean change, say at point U1, then you can imagine the left window average versus the right window average, the difference will be relatively large. And this is assumed, well, if the difference is large, we might think of, okay, there is a break at location U1. So similarly, as the window well changes, if there is no break, you can imagine the window difference might be small. So this is a basic idea about moving sum for change point detection. And here is so here the formula here is just, well, the left-hand side is this is the left window average, and then we minus the right window average, and this difference is well close to D1. D1 is the jump size at U1. So essentially D1 will be the signal together with those random noise. So this is the simple picture to illustrate the idea of moving sum. So what's the challenge here? Well, the challenge for MOSAM here, there are several challenges here. So one is, of course, that we consider high-dimensional time series. Another important thing is that, well, for this moving window, the window size is hard to determine in advance. So why the window size is hard to determine? Well, because so let's go back to the previous picture. So you can see that if the jump size is relatively large, then, well, you can use a quite small window size to detect the break location. However, if the jump size is relatively small, in order to find the break location, you might need a relatively large window. And also, so that means that you probably want to consider as a larger window size as possible. However, you cannot use a window size which is too large, because as you can see here, the basic idea here, within one window, we do not want to consider two bricks within one window. So we hope there's only one brick within one window. So that is to say, if your window size is chosen too large, and then it can incorporate two potential bricks, then the signal might cancel out, and you might, well, falsely detect or ignore certain signals. So this is not something we want. That is to say, we cannot allow the window size to be too large. However, well, because we do not want to incorporate more than one bricks. However, we don't want the window size to be too small because those small signals might not be able to be detected. So this is a very challenge for the idea of moving some. So what we are going to do here is that we want to introduce an adaptive move-some algorithm, so which allows the window size to be different for different bricks. However, pay attention here because we do not know the signal size in advance. So this is so that means the window size needs to be data adaptive. And another important contribution here is that we want to consider a high-dimensional time series with possible temporal and cross-sectional dependence. So this is makes the problem itself more challenging. So so before I move forward to the model here, a short idea about for high-dimensional time series in general. People need to aggregate the information so that we can deal the high dimensionality. And the aggregation, there's two very popular way of aggregation. One is L2 based, the other is L infinity based. So L2 based method is, well, you can imagine it's better for more dense signals. So while L infinity based aggregation is better for very sparse signals. So here, the two pictures here is an illustration about, so we are changing the proportion of components that consist jumps, and the Y label corresponding to the power using L2 based method versus L infinity based method. And you can see that, well, for P, we are changing P. And you can see that the two pictures, they all have very similar patterns. So the L2 based method immediately dominates the L infinity based method when the proportion of jumps exceeds certain, well, proportion. So and the proportion actually pretty small, and the L2 based method is pretty works much better than L infinity based method. So that's why here we propose to consider L2 based aggregation. Well, later on I will also mention the two-way aggregation, which handle the situation where the bricks does not happen simultaneously for all time series. So it's called dense or clustered signals. So those we will discuss later. So now let's look at the model. So the model here is quite standard. So we consider our observation YT to follow a mean plus noise model. So mu here corresponding to the trend and epsilon here corresponding to the random noise. And suppose the trend consists of k change points where the k here for sure is not given. And the mu here consists a two part. The first part is mu0. So mu0 is the trend where there is no breaks. And the other part here corresponding to the bricks, and we have k different bricks and with brick size gamma k at location UK. So first, first let's look at the first goal that we want to handle. So detect the existing bricks, and the idea here is that we consider testing the existing bricks under the null hypothesis where there's no brick at all, and we want to consider more than one bandwise. Well, this is important in order for our adaptive approach. So we consider a set of bandwise, which is B1 to BH, corresponding to H different bandwise. And we are going to, consider, all the bandwise. And well, the rough idea is similar to the most classic mode sum. So we can, so for each time point, we look at the left average versus the right average, and you can imagine their difference will be 0 if, well, the trend difference will be 0 if there's no break, and it will be gamma k if there is a break. So this is our test statistics. So we will consider the left average, the right average, and look at their difference. And we will standardize the difference using some lambda inverse, where lambda is a diagonal matrix. So this is standardized. And then we multiply by the, well, window size, and we consider the maximum over all the time points and take a maximum over all the bandwidth. So this is our basis test statistic for the null hypothesis. So the idea is that, well, under the null hypothesis, our test statistic will be very close to a Gaussian vector. So here Z here. And well, this Gaussian approximation is valid, well, under certain conditions. And this approximation is important because based on this approximation, we can determine the quantile for Qn, and then which will be used for the testing purpose. So we will reject the null hypothesis if the Qn statistic exceeds the threshold. And under null hypothesis, it should within the threshold. Well, so this approximation is used for our inference purpose, and will be later used for testing purpose as well. Here, the Gaussian vector here, Z, actually everything is known. Okay, so this Z is totally determined, so there's nothing to need to be estimated here. So this is very good for us in order for testing purpose. And so here is just so Q and alpha is just what I mentioned before, that here is the 1 minus alpha quantile of the Gaussian. And then we can reject our null hypothesis if Qn exceeds the Q alpha. Well, I will skip the theory here. So essentially this theory tells us that under null hypothesis, we will have this Gaussian approximation. So theorem 2 is, so theorem 1 is the case, well, where we do not consider the dependence. Here is case 2 is that under the dependence what will happen. So the same conclusion will hold, but with a little bit different conditions and assumptions. And here this is just saying that under certain regularity conditions, the test statistics power will go to 1. All right, so, well, next, I will move forward to talk about the how we estimate the break location using this idea. So this is a picture to illustrate our method. So as you can see before, that we have our statistic going over all the time points, and well, we go through several window size. So this picture, each point corresponding to one statistic at the location time I, and the corresponding window size. So this is a picture here, and the gray area corresponding to all the points that exceed the threshold. And what we do is that, well, we start from the smallest window size and we keep moving up. And we will, for each window size, we select the corresponding point that is the largest, and we will think of it as a potential break location. And then we will consider an area. So this is, say this is a blue area. So those are the areas where, well, all the points within the area will be influenced by the signal here. So we will delete all those points within this window. And then among the rest area, we will keep moving up the window size and find the second largest points outside the window, and keep doing that until there is no points outside those windows. So using this approach, you can see that we allow the bandwidth to be different for different break locations, And actually in this simulation here, the first break location here, the jump size is relatively small comparing to the rest. And we need to use the larger bandwidth in order to locate the break points. If we start with the relatively small bandwidth, there's no way for us to identify the break location. However, here you can see that we can identify the break location using larger bandwidth. So this is roughly the idea about how we adaptively choose a bandwidth based on this approach. So for different signals, we can have different bandwidths, and this can, well, better allocate the breakpoints. So let's move forward. So this is just some result about the consistency. And next, I just want to very briefly mention the two-way idea. So as mentioned before, I aggregate all the information together. However, this is not very powerful if there's only a proportion of signal jumps. So here is a picture comparing the two situations where the proportion of jumps are different and the power performance. So to consider the possible situation about only a proportion of time series jumps, we want to take into account those location information as well. So which means, well, instead of aggregating all the time series, we might want to only aggregate a group of data. So here, this is what we do when we try to only aggregate a subset of groups, the BL here corresponding to the subsets. And well, let me skip those dependence assumptions. So here, this is a picture to illustrate ideas. So essentially, instead of moving a window, only consider temporal windows, we consider a two-way window. So not only the temporal direction, but also spatial direction. So using this two-way window, so we move all the window together and consider several different possible group size. Then we are able to better aggregate the information spatially, which might enhance the power if not all the time series jump simultaneously. So this is our idea for two-way MOSA. So similar as before, the two-way MOSA, we still have the Gaussian approximation, based on which we can, well, use very similar ideas before to identify all the breaks. So here, this is another picture to illustrate our ideas. So we actually use our method on some data that are used before, try to locate all the breaks, and we seems can well, successfully locate all of them. So using this adaptive window idea. This is another picture. Okay, so let me sum up. So the rough idea here is that we try to consider an approach which can contribute when we can have a data-driven bandwidth selection. And also we consider two-way aggregation so that we can consider not only the temporal, but also the spatial signals. Well, if it's not all the sequence jump simultaneously. So that's all about this talk. Thank you.
Thanks, Lika, for the great talk. So we will postpone the Q&A to the end of the session. Now let me introduce our last speaker. Our last speaker is Dr. Dana Zhang. She is currently an assistant professor at the Department of Math at University of California, San Diego. Please join me welcoming Dr. Zhang.
Thank you, Mayu, for the nice introduction, for the invitation. And today I'm going to talk about the test of independence based on generalized distance covariance. Sorry, so let me share it again. Okay, now works. Test of independence is a fundamental problem and has a long history. We see a lot of methodologies to test for independence between two random variables in many classical textbooks on mathematical statistics theory. In modern statistics, it is also very powerful. It is also a very powerful tool in many research topics related to multivariate analysis or even high-dimensional analysis. For example, after fitting the linear regression, one essential step is to test if the residuals we obtained are independent of the covariates, where the covariates can be high-dimensional. Another example is sure screening. If there are a large number of covariates, and we hope to select all the important variables that are highly correlated or have high dependence with the response. So basically, we can design a test of independence under appropriate criteria. Another naturally related direction is independent component analysis in signal processing. It focuses on separating a multivariate signal into independent components. So we are considering this general problem, test the independence between two random vectors with their dimensions indexed by P and Q respectively. The story starts from the one-dimensional case. Some popular and classical methods include the ones based on contingency table, such as the well-known Pearson's chi-square test and the Fisher's exact test. And the rank correlation, such as the Spearman-Rho coefficient and the Kendall-Storr coefficient, using a measure of similarity of the ranking of the data. Some other well-intuitive methods can be based on the distribution function, characteristic function, and the likelihood. In the multivariate case or the high-dimensional case, the multivariate adaptation of these methods can cause a problem. For example, the rank-based methods will miss some affine property and cannot deal with the cases of non-monotone dependence. And the likely ratio-based methods are not applicable when the dimension is larger than the sample size or when the distribution assumption does not hold. So in our work, we study the generalized distance covariance. It is a feasible framework for the dependence measure of two random vectors of arbitrary dimensions. Before introducing it, let me briefly introduce two important and widely studied subclasses. One is distance covariance. It is firstly introduced by Zackley and his co-authors in 2007. It is defined as the weighted L2 norm of the distance between the joint characteristic function and the product of the marginal characteristic function of two random vectors. And this weight function is chosen to produce a scale equivalent, equivariant, and rotation invariant measure. And it does not go to zero for dependent variables. It is worth to mention that this distance covariance has the nice equivalent expression in terms of the classical covariance. And this formula provides a way of a very easy way of computation and estimation. And in machine learning literature, the widely studied is a kernel-based independence measure called the Hilbert-Schmidt independence criteria. And the central idea is embedding the joint distribution of the and the product of the marginals into a reproducing kernel Hilbert space and define the Hilbert-Schmidt independence criteria as the square of the square distance between the embeddings. So here are some basic properties. Firstly, it is non-negative. And if the two kernels, we call them characteristic, that means the HSIC is going to be zero if and only if the two random vectors are independent. And the commonly used kernels are the Gaussian kernel or Laplacian kernel. So we would say both of the two measures are covered under our framework of generalized distance covariance. It is induced by metrics. So we assume rho x and rho y be two metrics and of the negative type. And then the generalized distance covariance, the distance covariance is defined as the summation of the three parts. And this generalized variance is a special case when we set the two variables to be identical. So the generalized distance correlation can be defined by the standardized version. And here are some properties. It is always non-negative, and it covers the special case when we choose the metric rho to be the Euclidean norm, and then the generalized distance covariance will reduce to the classical distance covariance. And if we set the metric in terms of some kernel function in this way, then we can also relate the generalized distance covariance with the HSIC we just introduced. So for this general case, we make some assumption. So we let the two metrics satisfies the covariance, the generalized distance covariance equal to 0 if and only if the two random vectors are independent. So it is the measure we introduce. And next, we are going to present some asymptotic distributional theory. And let's first record the definition of the generalized distance covariance. So in principle, it consists of three components. And now, based on the ID samples, so it is the sample from the joint distributions. If we want to provide some unbiased estimator, one natural way is to consider the unbiased estimator for each of the three parts. So now we are considering the U-type unbiased estimators. For each part, we are considering some distinct pairs for the index, and then we use the sampled version. So when we consider the U-type estimator for each of the parts, then we just combine the three parts and produce some unbiased estimator for this general distance covariance. And with this unbiased estimator, let me introduce some existing results. So with this estimator, some earlier results include in the fixed dimensional case. That means when the dimension is quite low and fixed, then we can say this scaled statistic, its limiting distribution would be a linear combination of the centered chi-square distributions. It's the result for the low dimensional case, while for the high dimensional case, when the dimension of the two random vectors, either the minimum of them goes to 0 or the maximum of them goes to 0. The two earlier results, they establish the normal convergence. So that means the standardized version will converge to a normal distribution. So as we can see, under different dimensional regimes, we can have different types of the limiting distributions. One is the linear combination of chi-square distribution, and another is the normal convergence. So it can impose some extra difficulty which type of the distribution we should use when we are applying the independence test in practice. And technically, I would say for the fixed dimensional case, the key idea is using the multivariate central limit theorem, while for the high dimensional case, it uses the martingale central limit theorem, and the things, it only works under the high dimensional setting. So that's why in the high dimensional case, we have the normal convergence. And in our work, we are focusing on the establishment of some unified distributional theory to avoid such dichotomous distribution theory. So here's our construction. We first consider some first order kernel U statistic for our test statistic, and then we apply the Hoeveling decomposition. So the key idea is we construct some double centering operator so that our generalized distance covariance can be written as a quadratic form plus some remainder. And for this quadratic form, as we can see, it's the possible summation for different pairs, and with each term is denoted by the product of the D in terms of xk and xl. So firstly, we would say, under the null hypothesis, when the two random vectors are independent, we have the quadratic form. It has the mean 0, and for the remainder, it is negligible compared to the main term, in the sense that when we consider the square of the absolute value, its expected value, it is a small order for the counterpart of the former. So that's why it is asymptotically negligible, and we only needed to consider the main term Q. And to deal with this Q, what we will do is considering the eigen decomposition for the operator we just defined. So here we just consider the ordered eigenvalue and the eigenfunctions for this operator, and then here's some basic properties. And now we are considering the Kronecker product between the two random vectors, the x1 and y1 here. And then we would transfer the quadratic form as the version in terms of the Kronecker product. In this way, we can just combine the index k and the index l so that each summand is just this infinite dimensional vector transposed another infinite dimensional vector. So now we have some elegant expression as the quadratic form. And then we will apply the Gaussian approximation idea to establish the asymptotic series for the generalized distance covariance. So here, what we will do is we just generate ID normal distributions, and for this normal distribution, we keep the same covariance structure as the term we see here. And then we define the Gaussian analog. That means in each component, we use the generated Gaussian vector to replace the random vector in our quadratic form. So with this Gaussian analog, and then we just define the two more quantities by taking the summation of the square for each eigenvalues. With some mild moment conditions, we can establish this distributional theory. We will show that the cohomograph distance between our test statistic and its Gaussian analog, the distance is quite small, with the error rate bounded by the defined moment here and divided by the order for the n, and n to the power delta over 2. And in the outside, there's another power. So here, essentially, we are just assuming the 2 plus delta's moment for the for our sample exists. And if equivalently, we can also consider the generalized distance correlation by considering this scaled version. Then in the Gaussian analog, it's also scaled by the fx and fy we defined here. So it's the basic result. And next, let's see our limiting distribution. There's no doubt that when we are considering this quadratic form, after defining those ID normal distributions, the limiting distribution, the format looks like the linear combination of chi-squared random variables. But with this limiting distribution, it can be further approximated by the normal distribution if and only if the Lindeberg's central limit theorem the Lindeberg's central limit theorem holds. So we will find the necessary and sufficient condition by letting the lambda 1 of x and the lambda 1 of dy divided by fx fy goes to 0. And this condition, it can be equivalent to the third power in the summation by finding the definition of fx and fy here. So now if we define these two terms as the notation expected value of some function in terms of x1 to x3, and this part is the counterpart in terms of y1 to y3, then we can just recall the symptotic non-distribution is normal if and only if this condition hold. So for this condition, then let's discuss how this condition can be satisfied. So if we consider the maximum of the two dimension goes to infinity, then this condition is necessary for the central limit theorem. Things in the fixed dimensional case, both of the two quantities will not depend on the dimension. So both of the two will be scalar. And if so, the product of the two will never go to 0. And then the central limit theorem will never be held. That's why the maximum of the two dimension goes to infinity would be a necessary condition for the central limit theorem. But the minimum of the two dimension goes to infinity may not be a sufficient condition for the central limit theorem. It is only the case that the minimum of the two goes to infinity, and so that this condition is held, then it will imply the central limit theorem. So in summary, our main theory provides a unified distribution. So for this limiting distribution, it can be either the central limit theorem type or the combination of the chi-square type. And this theory is held under mild moment conditions, and it applies to arbitrary dimension cases. And next, I'm going to introduce a half permutation procedure. So let me recall the oracle procedure. If the distributions are known, then we just generate the samples from the known distributions, and then we compute the test statistic and make the decision. And right now, based on the samples, since the true distribution is unknown, so we are going to use a new half permutation procedure. The key idea is we choose a subset from the 4-index set, and then we combine the index 1 with the remaining set. So here 1 is combined with 2 and 3 combined with 4. And similarly, 1 can also be combined with 4 and 3 combined with 2. In this case, we can find that also x1 and y1 may be dependent, but x1 and y2, they must be independent. So we are going to generate the ID samples. So the half permutation means that we just choose half of the sample size to consider our index set, and then its complement. In this complement, we do the permutation. So in total, there would be n factorial over n factorial cases for when we consider this subset of psi cardinality m, and then for its complement, we use the permutation. And for each subsample, we calculate our test statistic and consider the empirical distribution function to determine the cutoff value we want to find in the hypothesis test. And another way we can compute is if n is large, then m as n over 2 is also quite large, then this factor can be very large. So we can also use the random half permutation procedure. So we just independently repeat the half sample for b times, and this b can be smaller than this large n. So here, it is the theoretical guarantee. We can show that the empirical distribution, it is close to the probability function of our test statistic, and with this additional assumption. So here, we just determine the cutoff value from this empirical distribution, and then make the decision if our sample generalized distance covariance is larger than the cutoff value we choose. Okay, so I will skip all the details and just introduce the simulation study. So we have two examples. The first example is like the autoregressive model of order 1, and the second example with the same covariance, it is more like the factor model. So as we can see, when we compare it with the central limit theorem, then we can find that others work, they would work well when dimension is very large. Since in the high dimensional case, under some certain condition, the central limit theorem works well. But for example 2, when there exists some strong factor, then the central limit theorem does not work. And our result, it will generate the valid, and it will generate the valid cutoff values. Thank you.
Thank you very much. We have time for like a question. Does anybody have any questions?
Thank you for the great talk. So during the interest time, we will end the session today. And thank you for your attention. Bye.